In the previous module, we have discussed about metrizable spaces. In the current module, we have discussed about topological spaces which are like metrizable spaces. For example, first countable space and stronger property second countable spaces. What is first countable spaces? Informally speaking, this is something like metrizable spaces. We have noticed a important property in first countable in metrizable spaces that a function is continuous at a point x if and only if for any sequence xn converging to that point x, if and only if the sequence fxn converges to fx. This continuity criteria for metrizable spaces is called Heinz continuity criteria. This criteria will also hold for metrizable spaces. And another condition that a point is a limit point of a set if and only if there exists a sequence xn in that set which converges to that point. We will observe that in first countable space both this property holds, and we will also see that there are spaces which are first countable but not metrizable. So let us go to slide presentation. As we have told, in this section we shall introduce some topological invariants which are closely related to metric spaces or metrizable spaces. Here we shall introduce first and second countability axiom and two of its consequences, namely separability and Lindelofness. The last two properties in general weaker than second countability. Also first countability also weaker than second countability. But in metric space we will show that Lindelofness or separability equal to second countability axiom. So let us start by the definition of first countable spaces. We already know what do we mean by a local base in a topological spaces. In fact, if X is a topological space and small x is a point in that topological spaces, by a local base we mean a collection of open neighborhoods of X such that for any open set U containing X, there exists some member of that collection, say capital N, such that X belongs to capital N is contained in that open set U. So this is called local neighborhood system or local base. In terms of local base, we will define first countability. A topological space X is said to have a countable basis at X if there is a countable collection script B of neighborhoods of X such that for any neighborhood of X containing small x, there exists at least one member from B which is contained in that neighborhood. That means a topological space is said to be first countable if at each point x there exists a countable local base. If a space X has a countable basis at each point, then it is called first countable space. Clearly, every metrizable space is first countable space. In metric space, in some point X, the countable local base can be defined as Bx1 by n such that n belongs to capital N. The most significant fact of first countability is that in such spaces, convergence sequence can determine limit point of sets and continuity of functions, which was known fact in metric spaces. Determination of continuity is called in metric space hence continuity criteria. So let us see the following theorem. Let capital X be a topological space. A subset capital A of capital X and a point small x is the limit point of capital A if and only if there exists a sequence in capital A converging to that point x. Also let f from x to y be a function. If f is continuous, then for every convergent sequence xn converging to x in capital X, the sequence fxn converges to fx. The converse holds if x is first countable. Let us come to the proof of the fact. The first part holds for every topological spaces. We shall omit its proof. For the second part, let us observe that for any point x, we can make a decreasing sequence of neighborhoods by taking Vn is equal to u1 intersection u2 intersection up to un, where un is a countable local base at x. In fact, by inductively we can define Vn. Then we get a decreasing sequence of neighborhoods of any point x, which is already available in metric space. Now let x be a limit point of a set capital A. We can choose some x1 belongs to A intersection Vn, as x is a limit point of capital A. Now inductively let x1, x2, xn be chosen. Then Vn plus 1 minus x1, x2, xn is an open set, as the finite set x1, x2, xn is closed and Vn plus 1 is a open neighborhood of x1. Now let x be a limit point of capital A. We can choose some point in the intersection of A and Vn. Let us call it x1. This is possible as x is a limit point of A. Now inductively let x1, x2, xn be chosen. Let us consider Vn plus 1 minus the set containing the points x1, x2, xn. This is an open set, in fact open neighborhood of small x, as the finite set x1, x2, xn is closed. Then as x is limit point of A, this open set of course meets A. So we can choose another point in A intersection Vn plus 1 such that another point is different from x1, x2, xn. Let us call this another point as xn plus 1. Thus we get a sequence xn in capital A which converges to x. Next we prove the condition which is called hence continuity criteria for metric space. In fact, the condition says that f is continuous at x if and only for any sequence xn converging to x fxn converges to fx. This part, the part that whenever xn converges to x, fxn converges to fx is true for any topological space and is obvious. We prove that if this happens, then f is continuous at x. If possible, f is discontinuous at x. This means that there is a neighborhood capital N of fx such that for any neighborhood m of x, fm is not properly contained in N. That is, there exists some point in f of m which is not contained in N. Since x is first countable, there is a countable neighborhood of decreasing sets, say m1, m2, m3. That means the sequence mn is a decreasing sequence of open sets containing x. But because the condition f of mi is not contained in N, we can choose xi from mi such that f of xi does not belongs to N, and we can choose such xi for each I belongs to capital N. Then the sequence xn obviously converges to x as the sequence mn decreases, but if xn is never in N, so in particular f of xn does not converges to fx. This theorem shows that first countable space always enjoys metric space like behaviors in case of continuity and convergency. Now we will discuss about the subspace and product of first countable space. Theorem: first countability is a hereditary property, and the part B, first countability is countably productive. To prove that first countability is a hereditary property, let us take Y as a subspace of capital X and small x belongs to capital Y. We have to produce a sequence of neighborhoods of X in the topological space Y. Now, as X belongs to capital X and capital X is a first countable space, so there exists a decreasing sequence of neighborhoods at X in capital X. Now let us take the trace of this neighborhood in Y. Then this trace gives a decreasing sequence of neighborhoods at X which becomes a local base. So we can say that first countability is a hereditary property. Now let us come to the proof of first countability is a countably productive property. Let xi be a sequence of first countable spaces and capital X be their product. Let us choose a point small x in the product capital X. Let bin such that n belongs to capital N is a countable local base at small xi in capital Xi, where small xi is the ith coordinate of x. Let capital Bn is equal to product of bin over I, and this is for all n belongs to capital N, and Bin is equal to xi for all I belongs to capital N except finitely many i's. Then the collection Bn such that n belongs to capital N gives a countable basis at x in capital X. Next, we come to define another countability axioms which is called second countability axioms. Most of the spaces we know are second countable spaces. In the future discussion, we will see that uncountable discrete spaces are not second countable. RL, that is Sargent-Frege line, is not second countable. Let us first come to the definition of second countable spaces. A space capital X is said to be second countable if it has a countable basis. It is easy to observe that R with its usual topology is second countable. In fact, the collection of all open intervals with rational endpoints becomes a countable base. This is very much clear that every second countable space is first countable. In fact, if X is second countable, then it has a countable basis, say Bn. Now, if small x is a point in capital X, then take all the Bn's which contain small x. This gives the countable local base at small x. Now, we will examine the similar property like first countability for second countable spaces. That is, we will verify that second countable space for every subset of second countable space is second countable, and second countability is countably productive property. Its proofs runs as almost first countable spaces. So, I am skipping this proof. I will advise the student to do yourself. So, in the proof of the fact that both first countability and second countability are countability productive property, you can notice that we have taken the product of the bases. Students can think that countable product of countable sets is countable, but I like to say that please keep in mind that this is not true. We have taken only finitely many of them, so they have become countable. So please warn yourself that countable product of countable set is not countable, that is uncountable. The following theorem will show that continuous image of first and second countable spaces. Theorem: if f from x to y is continuous open map from x to y and capital X is first countable respectively second countable, then y is so. Proof: we prove the case of second countability only, the first countability case will be same. So, let Bn such that n belongs to n be a countable basis of capital X consisting of open sets. What we have to show that just if Bn is a countable base of capital Y. Since f is given open mapping, then f of Bn's are all open sets. Now let Y belongs to capital U, where capital U as open set in Y. Then F inverse U is open in capital X as F is continuous. Since capital Bn is a countable basis, then we can choose some member of this collection, say capital B, such that X belongs to B subset of F inverse U, where F of X is equal to Y. Then clearly Y belongs to F of B is contained in U, and we have already told F of B is open as F is an open map. This shows that F of Bn such that n belongs to capital N is a basis for Y. We shall mention two important facts regarding second countability. We know that for a second countable space, not every basis is countable. For example, in the second countable space capital R with usual topology, the collection of all open intervals is not countable. But in a second countable spaces, every basis contains a countable basis. We can prove this in this way. Let Bn be a countable basis of a second countable space, and let script C be a basis. Then for every pair of indices n m for which it is possible, let us choose some Cmn belongs to script C such that Bn contained in Cmn which is contained in Bm. Then this collection Cmn gives a countable basis of the space X contained in the collection script C. Next, we have observed that every uncountable set in capital R with usual topology contains uncountably many limit points. The following theorem says that this result holds for every second countable space. Theorem: any uncountable set in a second countable space has uncountably many limit points. Proof: let A be an uncountable set in a second countable space. Since second countability is an hereditary property, so A is also second countable. Now, if possible, A have only countably many limit points, then all other points are isolated points. That means A has uncountably many isolated points. So, if we take the subspace topology on that uncountably many points, we get a discrete space which is not second countable, which contradicts the fact that every subspace of a second countable space is second countable. Next, let us come to the separable space. We have observed in case of R that Q is dense in R, where R is considered with the usual topology. That means R contains a countable dense subset. Those topological space which contains countable dense subset, we call them separable spaces. So, R is particular example of a separable topological spaces. An interesting example of a separable topological space is the collection of all real valued continuous mapping defined on the closed interval 0 1, which we denote by C01. Now consider the set of all polynomials with rational coefficients. We know that polynomial functions are continuous. So, every polynomial with rational coefficients restricted to the closed interval 0 1 belongs to the set C01, and this is a countable set. Now, by Vasta's approximation theorem, we know that this set is dense in 0 1. So, C01 is a separable space. So, what is the relation with second countability and separability? It can be proved that every second countable space is separable. The proof is very easy. In fact, if X is second countable, take a countable basis Bn and choose a point from each Bn. That will give us a countable dense subset. In case of metric spaces, we can prove that if it is separable, then it becomes second countable. The proof can be best shown by the diagram given here. Let X be a metrizable space and let capital A be a countable dense subset. Since capital X has been considered as separable space, we can find such a space. Then we can choose a sequence A is equal to A n I such that I belongs to I in capital A such that A n I converges to A. Then we can choose some A n k such that D A n k less than R. Let us rename A n k as X. We claim that B A I 1 by I such that n belongs to n, capital I belongs to I is a countable basis of X. For this, let us choose some y belongs to capital X and consider the open ball BYR. Then we can choose a sequence A is equal to A n I such that I belongs to I in capital A such that A n I converges to I. Let us choose some A n k such that D A n k less than R by 2. Let us rename A n k as X as shown in the picture. Since D A x less than R by 2, we can choose some m belongs to capital N such that D A x strictly less than 1 by m less than R by 2. Then clearly y belongs to B A n k comma 1 by n subset of B y R. This completes the proof. Separable metric space. One may expect that above result holds for first countable space also. That is, a first countable separable space is also second countable. But this is not true in general. In fact, it can be shown by the following example. Sorgenfrey line. the Sorgenfrey line RL is first countable. In fact, at any real number R, the collection from R to R plus 1 by n, where the right side is open, is a countable local base at R. So, RL is first countable. RL is separable also. In fact, Q is a countable dense subset of RL, but RL is not second countable, it has no countable basis. If possible, let script B be a countable basis of RL. Choose for each x an element Bx of script B such that x belongs to Bx subset of x to x plus 1, right hand side is open. Now, if x not equal to y, then clearly Bx not equal to By. Since x is equal to infimum of Bx and y is equal to infimum of By, so Bx not equal to By. Therefore, script B must be uncountable. The following theorem can be proved easily. The continuous image of any separable space is separable. An open subspace of separable space is separable. We are omitting the proof because it's very much easy. So, in the previous theorem, I have told that open subspace of separable space is separable. So, the question is whether every subspace of separable space is separable. The answer is no. We can prove that not every subspace of separable space is separable. In fact, Sorgenfrey plane, that is RL cross RL, is a separable space, but it has a non-separable subspace. For the proof, let us first say that finitely many product of separable space is separable as finite product of countable sets is countable. So, RL cross RL is a separable space as RL is in fact separable. Now, consider the line L is equal to all x minus x such that x belongs to R in RL cross RL. Then this line has discrete topology as a subspace of RL2. In fact, if we take any point x minus x on that line L, then we can see that x to u Cartesian product minus x to v is a rectangle in RL2 which is open in RL2 meets capital L only at the point x minus x. That means x minus x is an isolated point on the line. That means x minus x is an singleton open set on the line, so the line has the discrete topology, but line is uncountable. An uncountable discrete space can never be separable. This shows that subspace of separable space is not in general separable space. So, in this module we have discussed some countability axioms, first countability, second countability and separability, and some of its interconnections. With this we close this module. Let us pass to next module.